Welcome to the solution to the work, power, and energy problem set, problem number 11. We have a ski jumper that starts from rest 50 meters above the ground on a frictionless track and flies off the track at an angle of 45 degrees above the horizontal and at a height of 10 meters above the level ground. Neglect air resistance. We need to find her speed when she leaves the track, the maximum altitude she attains after leaving the track, and where she lands on the ground relative to the end of the track. This is a really neat AP problem that's going to incorporate a lot of different concepts rolled into one. If we take a look at the picture here, just a side note, this is a picture of the actual ski jump at Lake Placid where the famous Winter Games were held, where USA beat the Russians in hockey. You can actually see this ski jump from the road as you drive through the village of Lake Placid, and as you look up, you realize these people are absolutely nuts, crazy. It's amazing how high they start and how steep that thing is. All right, let's start with a good diagram here. We're going to let this represent the level ground. We have a ski jump that comes down. We're told this is 50 meters above. We're told this is 10 meters above the level ground. Initial velocity here is 0. One of our jobs is to find her velocity here and at 45 degrees to the horizontal. And so we'll start there. Clearly the phrase that the track is frictionless is a dead giveaway here, that you want to implement conservation of energy to find her velocity when she leaves the track. We're going to establish the base level to be the end of the track 10 meters from the ground for ease of calculation. We start with our conservation of energy expression, EO equals E. In the initial state at the top of the track, her mechanical energy is all in the form of gravitational potential, since her velocity is 0. Therefore, the initial mechanical energy is mgho. When she leaves the track, because we've selected the end of the track as the base level, her only mechanical energy there is kinetic. There obviously is another way to do this problem, in which her mechanical energy would be the sum of kinetic and potential at that spot if you select the level ground as the base level. We go ahead and we substitute. Mass cancels, so we have 9.8 times 40 as the initial height, the 50 minus the 10, equals 1/2 v squared. In doing the calculation, we should get v equals 28.0 meters per second. Go ahead and add that to our diagram, 28.0 meters per second. And the next part of the question, clearly what they want, the altitude after leaving the track and where she lands on the ground relative to the end of the track. Both of those are projectile motion questions. And so to do that, we're going to need to know the components of this velocity. And this would be 28 cosine of 45 degrees. And this would be 28 sine of 45 degrees. Okay? To find her height above the level ground, her maximum altitude after leaving the track. So she's going to fly off of here. Okay? And what we want is this maximum XY value in C. Just let's label it now. They're asking us for the range. Okay? All right. So, the skier is now a projectile. And to find that XY value, we know her velocity at the peak of the flight vertically is 0. We know the initial Y component. We know G. We can solve for XY. 0 squared equals 28 sine of 45 squared plus 2 times negative 9.8 times XY. We have conflicting directions in this problem. The 28 sine 45 component is up while the G value is down. Therefore, we have to account for that with a negative sign on the 9.8. We go ahead and we calculate XY, which is 20 meters. However, this is the XY value from the end of the track. So to get her maximum altitude, we're going to have to add in the 10 meters for a total of 30 meters of altitude above the ground. For part C, we need to know the range. And the only equation that we have to do that is Vx equals xx over t. We have the Vx component. What we don't know is the time in the air. So we have to do a calculation to find the time in the air. And the time in the air is determined by the vertical motion. So we'll use our xy equals voit plus 1/2 gt squared. This is a critical point here in calculating the correct answer for C, is that the displacement from the end of the track to the end of the event is negative 10 meters. She ends up negative 10 meters below where she started from. So we go ahead and we end up with a quadratic, which we'll go ahead and solve for. And the only positive root that we get from that is 4.49 seconds. The negative root we would ignore. From Vx equals xx over t, solving for xx, that would be Vox times t. Xx would be 28 cosine of 45 times the time, which we found to be 4.49 seconds. And our range we find to be 88.9 meters. Okay? And all of this was for part C. All right? There you go. There's your explanation of number 15. We will be doing number 16, the infamous Tarzan and Jane problem, in class tomorrow.